Hello everyone, welcome to the next section, Introduction to Convolutional Neural Networks. Convolutional neural networks, or CNNs, are everywhere. In the last 5 years, we have seen a dramatic rise in the performance of visual recognition systems due to the introduction of deep architectures for feature learning and classification. Now we will move on to the first video of this section that deals with convolutional neural networks. Let's begin with convolutional neural networks. You can observe in this image, a regular neural network receives input data as a single vector and passes through a series of hidden layers. Every hidden layer consists of a set of neurons, wherein every neuron is fully connected to all other neurons in the previous layer. Within a single layer, each neuron is completely independent, and they do not share any connections. The last fully connected layer, also called the output layer, contains class scores in the case of an image classification problem. Generally, there are 3 main layers in a simple convnet. They are the convolution layer, the pooling layer, and the fully connected layer. In the case of real-world image data, CNNs perform better than multi-layer perceptrons, MLPs. There are 2 reasons for this. Unlike MLPs, CNNs understand the fact that image pixels that are closer in proximity to each other are more heavily related than pixels that are further apart. Also represented as CNN equals to input layer plus hidden layer plus fully connected layer. CNNs differ from MLPs in the types of hidden layers that can be included in the model. A convnet arranges its neurons in 3 dimensions: width, height, and depth. Each layer transforms its 3D input volume into a 3D output volume of neurons using activation functions. Let's see, how do computers interpret images? Essentially, every image can be represented as a matrix of pixel values. In other words, images can be thought of as a function, f, that maps from R2 to R. In practice, the value of the function ranges only from 0 to 255. Similarly, a color image can be represented as a stack of 3 functions. We can write this as a vector of this equation, or we can write this as a mapping with this equation. So, a color image is also a function, but in this case, a value at each x, y position is not a single number. Instead, it is a vector that has 3 different light intensities corresponding to 3 color channels. Let's look at code for visualizing an image. Here, we will see the details of an image as input to a computer. Let's take a look at how an image can be visualized. For that, first we will import all required libraries. Then, we will include this block of code to load a color image in grayscale and specify path of the image. On executing the code, this image will be generated as a result. Further, we will execute another code snippet and observe the obtained image. Great! As you can see here, we can see another example with background is covered with digits. In the previous section, we used an MLP-based approach to recognize images. Let's look at 2 issues with that approach. It increases the number of parameters. It only accepts vectors as input, that is, flattening a matrix to a vector. This means we must find a new way to process images in which 2D information is not completely lost. CNNs address this issue. Furthermore, CNNs accept matrices as input. Convolutional layers preserve spatial structures. First, we define a convolution window, also called a filter or kernel. Then slide this over the image. Next is dropout. A neural network can be thought of as a search problem. Each node in the neural network is searching for correlation between the input data and the correct output data. Dropout randomly turns nodes off while forward propagating, and thus helps ward off weights from converging to identical positions. Let's look at convolutional layer. The main objective of convolution in relation to convnet is to extract features from the input image. This layer does most of the computation in a convnet. Now we will experience convolutional layers in Keras. To create a convolutional layer in Keras, let's first import the required modules with the code shown on the screen. Then we will create a convolutional layer by using the format displayed here. Let's understand these arguments in detail. So the filters specify the number of filters. Kernel size is number specifying both the height and width of the square convolutional window. There are also some additional optional arguments that you might like to tune. Strides, the stride of the convolution. If you don't specify anything, this is set to 1. Next is padding. This is either valid or same. If you don't specify anything, the padding is set to valid. Activation. This is typically ReLU. If you don't specify anything, no activation is applied. You are strongly encouraged to add a ReLU activation function to every convolutional layer in your networks. When using your convolutional layer as the first layer, appearing after the input layer in a model, you must provide an additional input shape argument, input shape. It is a tuple specifying the height, width, and depth, in that order, of the input. There are many other tunable arguments that you can set to change the behavior of your convolutional layers. In order to build a CNN with an input layer that accepts images of 200 by 200 pixels in grayscale, in such cases, the next layer would be a convolutional layer of 16 filters with width and height as 2. As we go ahead with the convolution, we can set the filter to jump 2 pixels together. Therefore, we can build a convolutional layer with a filter that doesn't pad the images with zeros. Run the code. Moving on to the next example. After we build our CNN model, we can have the next layer in it to be a convolutional layer. This layer will have 32 filters with width and height as 3, which would take the layer that was constructed in the previous example as its input. Here, as we proceed with the convolution, we will set the filter to jump 1 pixel at a time, such that the convolutional layer will be able to see all the regions of the previous layer too. We will run this code. Finally, we will look at the final example. You can also construct convolutional layers in Keras of size 2 by 2 with 64 filters and a ReLU activation function. Here, the convolution utilizes a stride of 1 with padding set to valid and all other arguments set to their default values. So let's execute it. As we have seen, a convolutional layer is a stack of feature maps with 1 feature map for each filter. More filters increase the dimensionality of convolution. Higher dimensionality indicates more parameters. So, the pooling layer controls overfitting by progressively reducing the spatial size of the representation to reduce the number of parameters and computation. The pooling layer often takes the convolutional layer as input. The most commonly used pooling approach is max pooling. In addition to max pooling, pooling units can also perform other functions such as average pooling. In a CNN, we can control the behavior of the convolutional layer by specifying the size of each filter and the number of filters. To increase the number of nodes in a convolutional layer, we can increase the number of filters. And to increase the size of the pattern, we can increase the size of the filter. There are also a few other hyperparameters that can be tuned. One of them is the stride of the convolution. Stride is the amount by which the filter slides over the image. A stride of 1 moves the filter by 1 pixel horizontally and vertically. Here, the convolution becomes the same as the width and depth of the input image. A stride of 2 makes a convolutional layer of half of the width and height of the image. If the filter extends outside of the image, then we can either ignore these unknown values or replace them with zeros. This is known as padding. In Keras, we can set padding equals valid if it is acceptable to lose a few values. Otherwise, set padding equals same. A very simple convnet looks like this.